We are now extremely close to the end of this entire course. And I'm actually done, believe it or not, with the technical part. The grand finale was really this idea that we could even make complicated systems like cars act like unicycles that we now know how to control and navigate around in complex environments, as we've seen both in theory, in simulation, and actually in real experiments. What I want to do in this sub-lecture is basically probe further. There are lots of things, believe it or not, that are actually not in this course pertaining to how to control robots. Here I have a picture of a praying mantis, and the reason for that is that we have not covered praying mantises. So I'm going to let this be a proxy for all the things we haven't talked about. Well, one thing that we haven't talked about is what happens when your system is generally nonlinear instead of linear. So we are now really, really good at dealing with linear control systems. Well, what if it is nonlinear? Well, we have dealt with some. We've dealt with the unicycle quite a bit. But there, we were kind of lucky that we had a lot of intuition. What if this is not the unicycle? What if this is massively nonlinear and strange and complicated? What do we actually do? Well, that's called nonlinear control. And it's not in this course, but I encourage you to keep educating yourselves and probing further along these lines. Another thing that we didn't deal with is what is called optimal control. So for us, the name of the game was stability. Stability. It was performance in the sense of tracking, right? So we wanted to track reference signals. And then we had robustness. But what we didn't have explicitly were things like this. So this is a general type of cost where we're saying, well, we want to minimize some cost involving X and U. This could be, the fuel consumed or the time it takes to get there, plus possibly some cost on the final point as well. This is known as optimal control, and this was also not in the course. So this is one grasshopper that we didn't see. There is another branch of decision theory known as machine learning that we didn't touch upon. And the reason why I'm putting this as another thing that you might want to probe further along is it's useful in robotics and it's highly related to control in general and optimal control in particular. So the idea is that I'm going to have some cost, V, and I'm going to have some policy pi, which says, what are you going to do when you're at a certain state? And the cost is just going to be a cost of the different, where I am at time k, and what I'm doing at time k. So this is really U sub k, right? And now I'm going to sum up this entire cost. And if you do that, you can write down something known as Bellman's optimality equation, or Bellman's equation, that basically characterizes what is the smallest you can make this cost. Well, it satisfies this kind of weird-looking expression. Right? And the point here is not the math. The point is that we have this equation, and machine learning is all about finding this V star by exploring, if I'm at this position, let's try doing U4. If I'm at another position, let's try doing U9. And while doing this, you're building up this V star cost function. And when you're done building it up, you all of a sudden have a complete map or guide to what should you do if you encounter a certain state. And that's, in a nutshell, what machine learning is about. Another thing that we didn't do much with is perception and mapping. We had infrared or ultrasonic range sensors, but a lot of times we have those, we have laser scanners, we have cameras. We did not deal with complicated sensing modalities, and we did also not deal with, okay, what do we do with all these sensor data? How do we actually produce maps of the world? Our world was, here is the robot, here's an obstacle, it's a point, let's just avoid it. But you know what? This obstacle may not be a point, it may be part of, I don't know, a corridor, and we would like to go in the corridor. Well, then it's good to actually describe what the world looks like. This is known as mapping. And again, this is a perfect opportunity for you to probe further, trying to build maps of the world. There are lots of different methods for doing it. And finally, the thing that we didn't do at all either is really talk about the high-level artificial intelligence. So how do you actually decide in the first place where you should be going? We said, given a goal point, how do we go there? But where did the goal point come from? Somehow, somewhere, someone is going to have to make decisions about what, at the very high level, the robot should be doing, and this falls squarely under the domain of artificial intelligence. Not covered in this course. I encourage you to probe further. So, to conclude, there are things that we haven't done in this class. There are lots of praying mantises that we didn't cover, right? And those are good things for you to probe further and learn more about. And if you know all of it, you can build an awesome robotic system. But beyond that, there are also lots of things we don't know. So here, not only praying mantises, but other green creatures. We have no idea what they look like. We don't know if they exist. We don't know what they are. It's the same with robotics. There's a lot of stuff going on that we as a community don't know how to do yet. So the last thing I want to do is give you the impression that this is a closed and complete case. We know everything about robotics. We don't. So not only in this course are there praying mantises, but outside of the course there are potential aliens that we still have not discovered.